Entropy is coined to describe microscopic configurations or microstates of a system. The more possibilities of microscopic configurations, the larger the entropy. Or the more microstates, the larger the entropy. Now, let's discuss it in detail. For a given microscopic system, for example, a system of a gas molecule, we use N, number of moles, T, temperature, P, pressure, and V, volume, to characterize it. But at the molecular level, microscopically, each molecule has its own kinetic energy, potential energy, that different from others. From a point of microscopic configuration, each molecule is distributed at a certain energy level. See the example shown in the slide. Suppose we have two identical molecules at the same energy level. The microstate of the two molecules is only one, as shown in graph 1. If one more energy level is presented, see graph 2, the molecules can redistribute at the levels given the molecule has enough energy to stay at a high level. For example, heating the system. Then the microstates of the molecule distribution go to 3. The number of microstates increase. Analogously, in graph 3, more energy levels, more microstates. If the molecules are different, see graph 4, the number of microstates increase more. So the entropy related to the microstates increases with the available microstates. Now, we talk about the macroscopic examples for microstates change. When molecule solid is heated up, it turns to liquid. The distance between the molecules increases. The molecules in liquid state move randomly. In contrast, the molecules in solid are immobilized. The molecules in liquid may have different velocity of motion, a different molecular vibration, different position from each other, and especially from that in liquid. Similarly, in gaseous state, the molecules have much more freedom. Due to the space increases, the higher kinetic energy and others. Again, entropy increases with microstates. How can we translate the microstates to entropy so that we can have a very clear view on a system? Use Boltzmann's equation. Boltzmann equation shows the entropy of a system can be calculated by counting the number of microstates. But for a real system, there are almost countless microstates. It's not possible using Boltzmann equation to calculate the entropy. Anyway, this equation does show us clearly the relationship between the entropy and the microstates. Till now, we learned that the number of the microscopic configurations of the microstates of the molecules increased with the number of molecules, increased with space available, the structural complexity of the molecules, the total energy, temperature, and etc. Each system at a fixed condition has its specific entropy that can be evaluated because the number of microstates is fixed. However, if we could know the entropy change for a process, it would be more straightforward that we can know immediately the entropy is increased or not. For example, ice at 0 degrees C melts into water at 0 degrees C. This is a phase change process. The formula used to calculate the entropy change are shown in the slide. In the formula, delta H is the enthalpy change for phase change, or say phase transition. If we have measured the delta H value for phase change, then we can calculate the entropy change value. We don't need to count the number of microstates.